All right, we're going to do some more basic differentiation rules, kind of see how we can apply these rules in different contexts to do questions that you might see pop up on an AP exam, either multiple choice or free response. All right, so sketch the graph of a function f such that the derivative f prime is less than 0 for all x, and the rate of change of the function is increasing. All right, so f prime of x is less than 0. Okay, so that means the slope is negative. All right, let's say slope of tangent lines are negative. All right, and then the rate of change of the function, is f prime of x. All right, remember rate of change, same thing as slope. All right, is increasing. So our slopes have to be negative, but they have to be increasing. Okay, so for the context of this problem, increasing means they get less negative. All right, now I'm going to use different words here in a second for those two, because there's an easier way to think about this, but using the words that we've gone over in class so far, this is what we're thinking about. Okay, so we're going to draw a function here. So slopes of the tangent lines are negative. So I want to draw something that starts high and goes low. Okay, but I also want those slopes to get less negative, less steep. All right, maybe let's use that word steep, less steep. All right, so if the slopes are increasing from a negative perspective, they're getting less and less steep. Okay, if you're positive slopes and you're getting increasing, then those are getting more steep. Okay, so it really depends on what the sign is to start with. Okay, so this could be an example of a function like that. All right, so the slopes of my tangent lines are negative. So if I draw tangent lines in here, they're all negative. Okay, even these over here that look like they might be going horizontal, I'm going to say that this graph is kind of like approaching an asymptote, going down little by little by little, even though it looks like it's getting flat. But they are also increasing. So this slope could be like -4, -3, -2, -1, -1/2, -1/4. So they're getting less and less steep, which means the negative numbers are getting greater. -4 is a smaller number than -1/4. Okay, so the slopes are increasing there. Okay, so a better way to think about this is when your tangent line slopes are negative, what is my function doing? What is this curve doing? Okay, this curve is going down. So when you see this right here, f prime is less than 0, that should tell you that f is decreasing. So in the future, when we see that, we're going to say, when I see this, I know it means this. Okay, so when I see derivative is less than 0, I know that that means original function is decreasing. All right, and so here, the rate of change of f is increasing. Okay, so the rate of change of the function is increasing. That tells me that this function is concave up. Okay, eventually we're going to take a second derivative of a function, and if the second derivative is positive, then that means f prime is increasing. So we can apply the same logic right here. So if f prime is negative, then f is decreasing. All right, so what if I did a second derivative? If the second derivative is, we'll do greater than 0 for this one, then that means that the first derivative is increasing. And that's what we want. F prime is increasing. Okay, and when the second derivative is positive, that's when you get a function that is concave up. Okay, we're going to cover this in more detail in a future lesson, but that's kind of a quick little reminder for those of you who've taken AB already, and a little quick lesson for those of you who haven't seen this yet. All right, so that's it though. This is our graph. That's going to be our answer for this problem. All right, next. Find A and B so that f is differentiable everywhere. Okay, so there's that word, differentiable. Differentiable means that the derivative exists for all values of x. All right, so what everybody does on this problem is they say, oh, f prime, I can take a derivative. So they do f prime of x is equal to, and this is not wrong. This is a good thing to do. So we multiply by the exponent. So we get 2ax to the 2 minus 1. So to the first power. So that's it. And then the plus 1, if we take the derivative, is 0. And so that is true when x is less than or equal to 2. And then they take the derivative here, and the derivative of bx is just b. Derivative of negative 3 is 0. And so that's true when x is greater than 0. Or sorry, greater than 2. All right, that's not incorrect. That's good. And so they're like, all right, well, I need to find a and b so the f is differentiable everywhere. And so whatever happens on the left has to be the same thing that happens on the right. So this is really a limit problem. You're going to do the limit as x approaches 2 from the left. And that's going to be of 2ax, because x is less than 2 there. And that has to equal the limit as x approaches 2 from the right. That's going to be of b, because that's where x is greater. And so you plug in 2 for x, and 2 times 2 is 4a. And then there's nothing to plug into here. Remember, this is x approaching 2. It's not b approaching 2. B is a constant. The limit of a constant is equal to a constant. All right, and so they've done everything correctly up to now, but now you're stuck. We have 4a equals b. We have 2 unknowns. There's no way to solve a single equation if you have 2 unknowns. Okay, to solve for 2 unknowns, you need 2 equations. So where does the other equation come from? Okay, you have to remember that definition of differentiable that we talked about that first day that we did it. Okay, so for f to be differentiable, if f is differentiable, therefore f is also continuous. This is a key thing for this problem. Okay, so before we can even say that the derivative is the same thing on the left and the right, we actually have to go to the original function. And we have to prove that this function is actually continuous at this point at x equals 2. Okay, I should say that it does say differentiable everywhere, and I'm really focusing in on only one point, x equals 2. But the reason I'm focusing in on x equals 2 is because this quadratic function, that is always continuous. And the derivative of that quadratic function is a linear function, which is always defined. Okay, this linear function is always continuous, and the derivative of that linear function is a constant, which is always defined. So the only place where this function could be not continuous or this function could be not differentiable is where they connect to each other, which happens at x equals 2. So that's why we're focusing in on x equals 2, because that's the only possibility where a discontinuity or a point where the function is not differentiable could occur. All right, so now we're going to go back to this function. We're going to do the same left-hand and right-hand limits over here. The limit as x approaches 2 from the left of ax squared plus 1 has to equal the limit as x approaches 2 from the right of bx minus 3. All right, so we're going to do direct substitution. Plug 2 in. 2 squared is 4, so that's 4a plus 1. Direct substitution over here, 2b minus 3. Okay, there's many different methods that you can do. I am going to choose to do substitution. So I am going to plug 4a in for b right there. All right, so that's going to be 4a plus 1 is equal to 2 times 4a minus 3. All right, so that's 4a plus 1 is equal to 8a minus 3. Add the 3 over here, subtract the 4a over here. A is equal to 1. B is equal to 4 times 1. B equals 4. All right, so if you plug these in, if I plug in 1 for A, I get 2x. And then you plug in 2. 2 times 2 is 4. And then if I plug in 4 there, I get 4. 4 and 4, same on both sides. Okay, over here, that's x squared plus 1. If I plug in 2, 2 squared is 4. 4 plus 1 is 5. If I plug in 4 for B, 4x minus 3. Plug in 2 for x. 4 times 2 is 8. 8 minus 3, 5. So it's the same on the left and the right. All right, so we've shown it's continuous. We use the definition of continuity. We use the definition of differentiability combined together, and we got our two values. All right, next problem. At time t equals 0, diver jumps from a diving board that is 32 feet above the water with an initial velocity of 16 feet per second. Use the position function, which they've given us here, where v naught is the initial velocity and s naught is the initial position. Okay, this right here is acceleration. Okay, these are for you physics people. Okay, this is acceleration, and it's acceleration due to gravity. Okay, whenever you have a projectile, something that you shoot up in the air, it could be your own body jumping off a diving board, it could be a ball you throw in the air. They're all going to apply to this general position function. Okay, so this is acceleration due to gravity. The acceleration due to gravity in feet per second squared, because it's acceleration, is actually negative 32 feet per second squared. And so this is actually half of that value. That's what goes into this equation right here. All right, so when does the diver hit the water? Okay, so S of t, diver hits the water when S of t, the position, is equal to 0. All right, hits the water, that is the x-axis, if you're thinking of it graphically. The water is the x-axis. All right, so we just need to set this equal to 0. I already have negative 16 t squared, and then we have a v naught, right? They told us initial velocity of 16 feet per second, so plus 16 t, and then initial position 32 feet above the water, plus 32. All right, we're going to do some factoring. So these have a 16 in common, and I also don't want a negative in front, so I'm going to take out a negative 16. So that's going to leave me with t squared minus t minus 2. Negative 16 t minus 2 times t plus 1. So that gives me t equals 2 and t equals negative 1. T represents time after the diver jumps. So time in this scenario can certainly not be less than 0, negative, so our answer has to be t equals 2. Find the instantaneous velocity when t equals 1. Okay, velocity, v of t, is equal to the derivative of position. Velocity is equal to the derivative of position. Okay, that is a relationship you will become very comfortable with if you're not already. All right, so v of t is equal to, so I have my s of t here in part A. I'm just taking the derivative of this. Multiply by 2, that's negative 32 times t to the first power. Multiply by 1, that's plus 16. And then the constant becomes 0 when you take the derivative. So this is our velocity function. And then they asked us to find the instantaneous velocity at t equals 1. So v of 1 is equal to negative 32 times 1 plus 16. That's negative 32 plus 16 is negative 16 feet per second. All right, I should have put my units on this answer, seconds. All right, part C, find the average velocity on the interval from 1 to 2. Okay, so this is where you have to have 2 points to do an average. It's like an algebra 1 style slope. Okay, they gave you the formula right here. So the average velocity is the difference in position divided by the difference in time. Okay, so we're going to do s of 2 minus s of 1 over 2 minus 1. So we already know s of 2. We got t equals 2 as our answer to part A, and that's when s was equal to 0. So s of 2 is equal to 0. We don't know s of 1, and we know the denominator is going to be a 1. Okay, so we'll just do s of 1 over here to the side. So negative 16 times 1 squared plus 16 times 1 plus 32. All right, well, that's negative 16, that's positive 16, so those cancel each other out. So this is equal to 32. 0 minus 32 divided by 1 is negative 32 feet per second. All right, so that's it for that problem. Kind of getting you started with some particle motion. That's what we're talking about here. and we'll get into that more in depth later. But getting that velocity is the derivative of position, that's kind of the big idea here. And that the average velocity is the change in position divided by the change in time. All right, on the back, we have a couple graphs. This is the graph of a position function. And this is then we have to draw the graph of a velocity function from 0 to 9. So remember, velocity is the slope of position. So our position function is a piecewise function with 3 lines. And so lines have a constant slope, constant rate of change. Okay, so that means our velocity function is going to have a lot of horizontal lines on it because it has a constant velocity. Constant means horizontal. You don't change. You don't have a slope. Okay, so let's see, 0, 1, 2, 3, 4, right there. 5, 6, 7, there, and then 9. Okay, so for the first part, from 0 to 4, we have to find this slope. So rise over 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So it's 6 over 4, which is 3 halves. So here is 3 halves. And it's going to be a horizontal line because the slope is the same all the way until we hit 4. So 1, 2, 3, 4, right there. And then I need to end it with some sort of circle. I'll talk about that in a minute. Let's do the other one. So this one from 4 to 7, the slope is 0. Horizontal line there. So we're down here at 0. 1, 2, 3. So this is 4. This is 7. 9's over here. All right, then the other one looks like 1 over 2. So 1/2. So here to here. Okay. Since this is piecewise, your circles, one has to be open, one has to be closed. And no one really agrees, like, should the endpoint be included in this slope or should it be included in this slope? All right, there's no agreement on that, so it really doesn't matter. Just make sure you don't put closed circles on both and you're fine. So open circle there, closed circle here, open circle there, closed circle here, and then we can end with a closed circle since that's our last point. All right, that'll do it for this lesson.